Ever wondered how negative numbers are represented in digital logic design? Well, let's unravel this mystery together. Digital logic design, or DLD for short, is a fundamental pillar in the world of engineering, powering the digital systems we interact with daily. We're talking about everything from our smartphones to the complex processors in our computers. Now, at the heart of these systems are binary numbers, sequences of zeros and ones. They're great for representing positive numbers. But what happens when we need to deal with negative numbers? After all, computations aren't always about positives, are they? In the digital world, we often need to perform calculations that involve negative integers. So how do we represent these negative numbers? That's where 2's complement comes in. 2's complement is a method used to represent both positive and negative integers in binary. It's a clever and elegant system that allows us to perform arithmetic operations with ease in digital logic design. Let's start with positive numbers. These are simple enough. We represent positive integers directly in binary, just as we do in unsigned binary representation. For example, the number 5 is written as 0101e and the number 10 as 1010. No surprises there. But what about negative numbers? This is where 2's complement truly shines. To represent a negative number, we firstly take the binary representation of its positive counterpart. Then we invert all the bits, changing zeros to ones and ones to zeros. Lastly, we add 1 to the result. For instance, let's consider the number -3. The binary representation of +3 is 0011. Inverting all the bits gives us 1100. Then we add 1, resulting in 1101. So, -3 is represented as 1101 in 2's complement. What about arithmetic operations? Well, when adding two numbers, whether positive or negative, we perform the addition just as we would in unsigned binary. Subtraction, on the other hand, requires a special procedure. We perform subtraction using binary addition, but we need to consider the concept of borrow. Let's say we want to subtract 3 from 5. We represent 5 as 0101 and -3 as 1101e, which is the 2's complement of 3. The result is 0010, which is 2 in decimal. This indicates that 5 minus 3 equals 2. However, be aware of overflow. Overflow can occur in 2's complement representation when the result of an addition or subtraction is too large or too negative to be represented with the given number of bits. In conclusion, understanding 2's complement is vital for designing digital circuits involving signed arithmetic, such as arithmetic logic units in processors. This ensures correct operations when handling both positive and negative numbers in digital systems. Now let's delve deeper into how exactly we represent negative numbers using 2's complement. Representing negative numbers using 2's complement involves a two-step process. Now let's delve deeper into this process. To represent a negative number, we start with the positive binary representation of the number. We then invert all the bits, changing zeros to ones and ones to zeros. Let's take a moment to visualize this. Imagine a string of binary digits, a mix of ones and zeros. In this step, we flip each bit. If it was a 1, it becomes a 0. If it was a 0, it turns into a 1. This is what we mean by invert. But we're not done yet. The second step is to add 1 to the result. This might seem a little counterintuitive, but it's an integral part of the process. Adding 1 to the inverted bits completes our transformation from a positive number to a negative one in the realm of 2's complement representation. Let's walk through an example to make this more tangible. We'll use the number -3 or -3. The positive binary representation of 3 is 0011. When we invert all the bits, we're left with 1100. And then comes our second step. We add 1 to this result. 1100 becomes 1101. And there you have it. In 2's complement, -3 is represented as 1101. It's important to remember that this process is not unique to the number 3. It applies to any negative number you want to represent using 2's complement. So why do we represent negative numbers this way in digital logic design? It's because 2's complement simplifies arithmetic operations, making addition and subtraction easier to perform in binary. With this method, digital systems can smoothly handle both positive and negative integers, ensuring correct operation. And just like that, we have represented -3 using 2's complement. Arithmetic operations in 2's complement are straightforward with a few special considerations. Let's delve into the fascinating world of addition and subtraction in 2's complement. Just as we do in our daily life, digital systems perform arithmetic operations. The beauty of 2's complement representation is that addition works just like in unsigned binary. Imagine we have two numbers, say 4 and 3. In 2's complement, 4 is represented as 0100 and 3 as 0011. To add these numbers, we simply perform binary addition, starting from the least significant bit and moving towards the most significant bit. The result is 0111, which translates back to 7 in decimal form. Easy, isn't it? Now let's move on to subtraction, which is slightly trickier but equally fascinating. Subtraction in 2's complement is performed using binary addition, but with a special consideration for borrow. Let's illustrate this with an example. Subtracting 3 from 5. In 2's complement, 5 is represented as 0101 and negative 3, which is the 2's complement of 3, is represented as 1101. When we add these two numbers together, we get 10010. However, since we only have 4 bits, the most significant bit is discarded, leaving us with 0010, which translates back to 2 in decimal form. That's right, we've just performed subtraction using addition. This is the magic of 2's complement. Now you might be wondering, what happens when we subtract a larger number from a smaller one? Well, in that case, the result would be a negative number represented in 2's complement. Let's take an example. Subtracting 5 from 3. In this case, we would get 1110, which is the 2's complement representation of negative 2. So, as you can see, arithmetic in 2's complement is quite similar to that in unsigned binary. With the understanding of addition and subtraction in 2's complement, we've uncovered another layer of the fascinating world of digital logic design. What happens when the result of an operation is too large or too negative to represent with the available bits? This is where we encounter something called overflow in 2's complement. Let's simplify it. Imagine you're trying to fit a gallon of water into a pint-sized glass. It's just not going to work, right? Similarly, in digital systems, overflow occurs when the result of an arithmetic operation cannot be represented within the available number of bits. For instance, if we're working with 4 bits and we add 7, represented as 0111, and 5, represented as 0101, we get 1100. But wait a minute, that's a negative 4 in 2's complement. This is a clear example of overflow. Overflow can have serious implications in digital systems, leading to incorrect results and potential system failures. Therefore, understanding overflow, how it occurs, and how to handle it is essential for avoiding errors in digital systems. Let's take a moment to recap what we've learned. In the intricate world of digital logic design, or DLD, negative numbers are often represented through a system known as 2's complement. This method has earned its place as the leading choice for representing both positive and negative integers in digital systems. The reason behind its popularity is its ability to simplify arithmetic operations. The process of representing positive integers in this system is straightforward. These numbers are directly translated into binary, mirroring how they would appear in unsigned binary representation. When it comes to negative numbers, the process is a bit more complex. First, the positive binary representation of the number is inverted, changing all the zeros to ones and all the ones to zeros. Following this inversion, 1 is added to the result. To illustrate, let's revisit the example of negative 3. Its positive binary representation is 0011. Upon inversion, it becomes 1100. After adding 1, the final 2's complement representation of negative 3 is 1101. Addition and subtraction in the realm of 2's complement are managed just like in unsigned binary. The only difference comes when subtracting, where a special consideration for borrow is needed. One potential pitfall to be aware of when dealing with 2's complement representation is overflow. This can occur when the result of addition or subtraction is either too large or too negative to be represented with the available number of bits. The understanding of negative numbers representation in 2's complement is vital for any digital circuit design involving signed arithmetic. It's a fundamental pillar in the architecture of arithmetic logic units, or ALUs, in processors, ensuring their correct operation when handling both positive and negative numbers. And that's how negative numbers are represented in digital logic design using 2's complement. Thanks for joining us today.